My name is Manturupa. Now I am going to briefly discuss on determining global states of distributed system. Actually, this paper is published by Mani Chandy and Leslie Lamford. So it's basically known as Chandy-Lamford algorithm. This paper presents an algorithm by which a process in a distributed system determines the global state of the system during completion. Many problems in distributed systems can be cast in terms of the problem of detecting global states. For instance, the global state detection algorithm helps to solve an important class of problems like state property detection. A state property detection is one that persists once a stable property becomes true, it remains true thereafter. Some of the examples of stable properties are computation has terminated, or the system may become deadlocked, all the tokens in a token ring have disappeared, like that. The stable property detection problem is that of devising algorithm to detect a given stable property. Global state detection can also be used in checkpointing. When we come across the distributed system, mm, we need to there are different process in the distributed system. There may be mm, a way to communicate between them. This paper presents an algorithm by which a process in a distributed system can determine a global state of the system during the completion. Processes in a distributed system communicating by sending and receiving messages. A process can record its own state and the message it sends and receives. To determine a global system state, a process P must enlist the cooperation of other processes that must record their own local states and send the recorded local states to P. All processes cannot record their local states at precisely the same instant unless they have access to a common clock. We assume that the processes do not share clock or memory. The problem is to devise an algorithm by which processes record their own state and the states of communication channels, so that the set of the process and channels states records from a global system state. The global state detection algorithm is to be superimposed on the underlying computation. The state detection algorithm, the detection algorithm plays the role of it's just like the mm, photographer observing a dynamic scene, such as like sky filled with migrating birds. So when we take that, a single photographer cannot take all the whole photo. A scene so vast that it cannot be captured by a single photographer. The photographers must take several snapshots and piece the snapshot together to form a picture of the overall scene. The snapshot cannot all be taken at a precisely same instant because of some of the synchronization problems. Further, and then photographers should not disturb the process should not disturb the other photographers. For instance, they cannot get all the birds in the heavens to remain motionless while the photographers are taken. The composite picture should be meaningless. The problem before us is to define the meaningful, and then to determine how the photographer should be taken. Before we go into the models, let's discuss something like uh, so like consider some let y be a predicate function defined on the global states of a distributed system D. That is, y of s is true or false for a global state s of D. The predicate y is said to be stable property of D if y of s implies y of s dash for all the global states s dash of D reachable from global state S of D. In other words, we can say that if y is a stable property and y is true at a point in a computation of D, and then y is true at all later points in that computation. uh, I already said some of the stable property examples are deadlock, system deadlock, and computation has terminated, like that. And some of the several distributed system problems can be formulated as the general problem of devising an algorithm by which a process in a distributed system can determine whether a stable property y of the system holds or not. Mm, deadlock detection and termination. Deadlock detection and termination detection are some of the special cases of the stable property detection problem. And some of the several algorithms are also come through for solving deadlock and termination problems, by determining the global states of the distributed systems. um, some of the algorithms have also came. One of the example is Gliger and Shattuck state. That so why those fail means some of the incorrect or impractical algorithms, maybe that has a relationship among the local process states, global system states, and points in a distributed computation are not well specified in those algorithms. So this Chandy and Lamport has tried to given out a better algorithm for this distributed systems. Uh, many distributed algorithms are structured as a sequence of phases where each phase consists of a transient part in which useful work is done, followed by a stable part in which the system cycles endlessly and uselessly. The presence of this stable behavior indicates the end of the phase. The phase is similar to a series of iterations in a sequential program, which are repeated until successive iterations produce no change. That is, stability is attained. Stability must be detected so that one phase can be terminated and the next phase is initiated. The termination of a computational phase is not identical to the termination of the computation. Now, when a computation terminates, all activities cease, messages are not sent, and process states do not change. There may be activity during the stable behavior that indicates the end of the computational phase, that messages may be sent and received, and process may change state. But this activity serves no purpose other than to signal the end of the phase. Actually, so there this paper we are they are concerned about with the detection of this stable system properties. Mm, uh, let's go to the model of distributed system. A distributed system consists of finite set of processes, and so one in the some of the processes in the one system and some of the processes in the another system. They need a way to communicate with them, synchronize with them. Oh, and a finite set of channels will be there. So they will going to communicate with the channels by sending messages and receiving messages. So they need a global state without the global clock. Well, we can also or show them by using the direct graph, in which we can say vertices will represent the processes and the edges will represent the channels. We can see in the figure. Mm, a distributed system with process P, Q are three processes. P and Q and R, those are connected by channels. P and Q are connected by C1. P1 can send messages through channel C1, and Q can send yeah, and also they send message to C2 channel, and C3 and C4 channel connects the P and Q with the channel R. They can communicate with these channels. The yeah then Channels, actually channels are assumed to have infinite buffers. They can send the message from one process to other process, and to be error free, and to deliver, as I already told, to deliver messages in the order that have sent from one process to in another process. The delay experienced by a message in a channel is arbitrary. It is random delay. So, but it is to be finite. So have to anyway data has to message has to send from process to other process. Mm, the sequence of messages received along the channel is an initial subsequence of the sequence of messages sent along the channel. The the state now you say, the state of a channel is the sequence of messages sent along the channel, excluding the messages received along the channel. This is the state of the channel. Mm, and then, process can be defined by a set of states, and a initial state, and a set of events will turn from one state to another state. Mm, Actually, an event E in the process P, let's consider an event E in the process. Let's consider process as P. Then atomic action that may change the state of P itself and the state of at most one channel. The channel can be considered as C incident on P. The state of C may be changed by the sending of the message along C or the receipt of the message along C. Anyway, the state can be changed by sending message. It can be changed, or by receiving message. A state can be changed. Mm, here the event E can be defined by 5 tuples. Here 5 tuple in this way, it's a derivation, not it can be said as it is a definition. P, here P is the process, and this C is the channel that's connecting the one process from one system to other system, and M is the message that is flowing in the channel. And S is the state of P that is immediately before event happened, and S dash, here S dash is state of P that is immediately after the event. Mm, uh, and a global state of a distributed system is a set of component process and channel states. The initial global state is one in which the state of each process in its initial state and the state of each channel is the empty sequence. There is no message initially. There will no message is sending across, and if the message is sent means it will change one state to another state. So global state will be varied. The occurrence of an event may change the global state. I already told E is so I already defined what is E. We may say E can occur in global state S. There are two properties that if and only if the state of a process P in a global state S is S, and if C is a channel directed towards P. The if actually if C is a channel directed towards P, then the state of C in global state S is a sequence of messages with M at its head. There will be a sequence of messages that so M is the head message, all the other messages will be that message. So we can so there are many messages. So here they are defined a function next, that way. So the next as shown in function next S of E comma S comma E, which is a global state immediately after the occurrence of event E in global state S. The value of next S comma E is defined only if event E event E can occur in global state S, in which case next of S comma V is the global state identical to S, except that we can the state of P in next of S comma E is S dash, or and if E is a channel that is directed towards P, then the state of C in next of S comma V is C state in S with message M is deleted from its head, and yeah, I will repeat once again. If C is a channel directed away from P means, then the state of C in next of S comma E is the same as C state in S with message M is added to the tail. Before that said that if E is a channel that directed towards P means it is the here message M is deleted from the head, but here in this case message M is added to the tail. This is a sequence SEQ of EI 0 to 0 less than equal to I less than equal to n, which is a sequence of events. Okay, a sequence of events in the component process of a distributed system. We say that this SEQ is a computation of a system if and only if that event EI can occur in the global state S of I, that if it is sequence will be with respect to the our system, that is computation, only if which is occur in our global state. If and only if occur in the global state, then those events will be can be considered in our system. We can also take as this SI here is SI can be taken as that global state can be represented as SI. So and here S naught is the initial global state, and I already told next of S comma about S next of SI comma E. So we can get the S of I plus 1 next state by using this formula next of Si comma Ei. We can use this formula to find next. So here I already told S naught is the initial state. And this is again one simple example of distributed system and state transition diagrams. Here this is two process P and Q. They are communicated with the channels channel C and C dash. P can send a message through channel C, and you can receive a message to channel C dash by the process Q. This is a simple example of it. Here these are all the two processes, and the system if actually the communication is through the tokens. Yeah, the system contains one token that is passed from one process to another, and hence here only one process token is there, so here it is called as single token conservation system. Each process has two states, S0 and S1. Actually two states. S0 is a state in which a process does not possess. If the process not having the token means it is in S0 state. If it is having the token means it is S1 state. If we pause, if it first it is in the S0 S1 phase, then it will pass the token to the other one, and its state will be dropped from S0 S1 to S0 like that. Each process has two events: a transition from S1 to S0 with sending of the token, and a transition from S0 to S1 with the receipt of the token. the this is the state transition diagram, how the state will be changed. We can see this. Next, this is the main thing. This is the global states and transition of the single token conservation system. At first, we can see first we can see we can track from any of these global state. First token is in P, so P is in S1 state. There is no token passing and everything, so it is shown as empty. So Q is in S0 phase, which is not having the token. So S0 is sending the token to P is sending the token to Q. So it will draw from S1 to S0. So you can see the figure in the above right corner. Token C, and it's not reaching yet. After token is reached to Q, its state will become S1. So and then what Q will do is it will pass the token to P, so its state will be become S0, and then the same process will be continued. This is the global states and transition of the single token conservation system. And then this is state transition diagram of process P and Q for non-deterministic computation. In the previous example, we have seen there is exactly one event possible in each global states. So process P and Q are defined by the state transition diagram. I have already shown how they are represented, but this can also be happen. So this is called as non-deterministic computation. Here what it will do is, here initial A is sending the message M to B, and it is receiving message M dash from B. So and then C is sending the message M dash to D, and then C is receiving the message M. So it's not a single event. Okay, both the events can be happen at a single time. So it is called as non-deterministic computation. Here this is non-deterministic how it will happen. So first there are many global states here. First initial global state S0, we can see in the diagram. So if P sends M, means there will be another global state. So after Q sends M dash, we will get the global state in the figure we can see. And after P receives the M dash, we got another global state. So here these are the events that are happen. So there should be a way to synchronize among them. They need a way to synchronize. We can't accept a single global state. By time to time global state will be changed, and every process need to know about this global state. So Lamport and Chandy tried to figure out the answer for this. Then motivation of the algorithm. Motivation for the algorithm. This global state recording algorithm mainly is designed by the Chandy and Lamport. They are designed in 1985 only. Based on that algorithm only, there are many researchers are happening now. Here, here main thing is each process records its own state, and the two processes that a channel is incident on cooperate in recording the channel state. Here we cannot ensure that the states of all processes and channels will be recorded at the same instant, because there is no global clock now. So however, we require the recorded process and the channel states or form a meaningful global state system data. Everything is dependent on this recorded process by the recorded process and channel states that is recorded by both the processes that sharing the channel. They are passing the messages between them. The global this algorithm may send messages and require process to carry out computations. However, the messages and computation required to record the global state must not interfere with the underlying computation. So they are going to considering an example through which they will how they will check how the motivation for this algorithm came in. Here what they take is they are record the state of the channel instantaneously. They and their channel same as C is the channel they have taken, and from P to Q they have taken a channel as C. And for the process P and Q, they are taking the single token reservation system. Actually, I already told about the single token reservation system. There is each process is sending the token to other process for like that single process conservation system was. State of the they are considered if state of the process P is recorded in global state in P, then the state recorded for P shows the token in P. So now they are assuming that the global state transits to in C. Suppose we can consider the states of channels C and C dash and of process Q were recorded in global state in C. So the state recorded for channel C shows it with a token, and the states recorded for channel C dash and process Q show them not in the position of the token. The composite global state recorded in this fashion would show two tokens in the system, one in the P and the other in the C. But a global state with two tokens is unreachable now. So from the initial global state in a single token conservation system, so there will be arise an inconsistency, because the state of the P is recorded before P sent the message along C, and the state of C is recorded after P that is sending the message. So so they are considering n number of messages sent along C before P's state is recorded, and let's consider n dash be the number of messages sent along C before C state is recorded. So suppose let's consider the state of the C is recorded in global state in P. The system then transits to global state in C, and then states of C dash P and Q are recorded in global state in C. The recorded global state shows no token in the system. So this is suggests that the recorded global state may be inconsistent if the state of the C is recorded before P sends a message along C, and the state of the P is recorded after P that is sending a message along C. So that is we can consider if n number of messages n is greater than, that is the n dash the number of messages that is sent along the C, that is before the C state is recorded now. So for a consistent global state we require the n number of messages. N is equal to n dash, and I already told what an n and n dash is, and we also require the m is equal to m dash, that is m and n are m and m dash are is shown here. Number of messages received along C before Q state is recorded, and number of m dash is number of messages received along C before C state is recorded. So in every state the number of messages received along the channel cannot exceed the number of messages sent the channel. This is to know. So n dash is greater than or equal to m dash. So this from we can see from these are all from these are all equations we can say that n may be greater than m. They also start make the two rules, that is one for global state detection. There is rules, that is marker sending rule for process P, where what it says for each channel C incident on and directed away from P. They are saying that P sends one marker along C after P records its state and before P sends further messages along C. Okay, okay. Then another state is marker receiving rules for process, that is process, another process, that is Q, and receiving a marker along a channel C. So if Q has not recorded its state, means what will Q will do is Q which is going to record its state, and Q records the state C as the empty sequence. So it is not recorded yet, so it will take as an empty sequence. If not, Q records the state of the C as a sequence of messages that is received along C after Q's state was recorded and before Q received the marker along the C. Then actually, then the marker, that is I already told what marker is. The marker receiving and sending rules guarantee that if a marker is received along every channel, then each process will record its states and the states of all incoming channels. To ensure that the global state recording algorithm terminates in finite time, each process must ensure that no marker remains forever in an incident input channel, and it records its state within infinite time of initiation of the algorithm. So I have to do directed graph is used for this. If the graph is strongly connected and at least one process spontaneously records state, means then all the process will record their states in finite time. The recorded process and channel states must be collected and assembled to form the recorded global state. Then let's go to the properties of the recorded global state. This shows the recorded global state diagram. Yeah, assume that the state of the P is recorded in global state S naught, and then so the state recorded for P is A. After recording its state, P sends a marker along the channel. Channel we can consider as C. So we can assume that the system goes to global state S1, S1 then S2 then S3, while the marker is still in transit and the marker is received by Q when the system is in the global state S3. So on receiving the marker, what the Q will do is it will record its state, which is D, that is already shown in the non-deterministic diagram. That is can show how here it is D. On receiving the marker, you can see on receiving the marker, Q records the state, which is D, and records the state of the C to as the empty sequence. After receiving his state, Q sends the marker along the channel C dash. So after on receiving the marker, after P records the state of the C dash as a sequence consisting of the single message M dash. The recorded global state we can consider as S star. I will show this. Sorry. Yeah, the recorded global state, which here you can take as S star or anything that is shown here only. and clearly observed that the global state S star recorded by the algorithm is not identical to any of the global state I have already shown over S naught, S1 and S2 and S3. I already shown the picture that occurred in the computation. For this, so we can consider the sequence. I already told about the sequence, that is the sequence of events, and this is here Si can be taken as the global state of the system immediately, that is before the event Ei. Let the algorithm consider algorithm initiated at the global state, global state S1, anything we can take, and let's terminate the global state at S at I have considered it as S at, and recorded global state as S naught. We can show that S star is reachable from Si, and Si is reachable from S star. So specifically speaking, that there we can see from this one, there exists a computation sequence dash, the so here sequence dash is a permutation of sequence that such that this initial state S and the terminate state S state and recorded global state S star occur as global states in sequence dash, and then this terminate initial state is equal to S star, or S star, or S star means recorded state, or it can be considered as initial state S dash, which is occurs earlier than our recorded state S star, and S that is S that is terminate state. Third point is that should be terminate state, not the static state. That is terminate should be recorded global state, or we can consider it as a recorded global state that is occurs earlier than this is earlier than the terminate state in SQ dash. So recorded state will be in the middle. So that is between the initial state and terminate state, we can consider it as. And now let's talk about some of the pre-recording and the post-recording events. If event Ei in sequence it can be called a pre-recording event if Ei is in the process P and P records state after Ei in the sequence. So this is the pre-recording event. Event, if the event Ei in the sequence can call post-recording event if and only if it is not a pre-recording event. So it is not a pre-recording event means it will be post-recording event. That is, if Ei in a process P and P records state before Ei in the sequence. So, this is the pre-recording and post-recording events. Then some of the pre-recording and the post-recording events that is in the figure. I will show that figure. In this figure. In this figure, we have listed out the pre-recording and the post-recording events. Here we can consider one event as E naught, that is P P sends a message M, sends M and changes state to B, which can be considered as post recording event, and then Q sends M dash and change state to D, which is pre recording event, and P receives M dash and change state to J, which is post recording event. So here I already first event, that is E naught, a post recording event I already told about, event that is immediately precedes the second event. I already told about the E1 event, that is sending of message M dash from Q, that is immediately preceding E1. So a post recording event, we interchange them to get the permuted sequence sq dash sequence q dash. Here in this permuted sequence, e naught dash first event can be considered as q a permuted one. We can I will say this first sequence is q sends m dash and change state to d, which is a pre-recording event, and then p sends m and changes state to b. This is a post-recording event, and then p receives m dash and change state to a, which is post-recording event. And then stability detection. This shows the stability detection algorithm. We are yeah the input and output are already given here. The input to the algorithm is a function y. During the execution of the algorithm, the value y of s for some global state s may be determined by a process in the system by applying the externally defined function like y to the global state s. But by the output of the algorithm, it is a boolean value. It means that some specially designed process like p enters and thereafter remains in some special state to symbolize an output of define is equal to true, and p enters and remains in some other special state to symbolize that that the output is something else, like definite is equal to false. This definite is equal to true means the stable property holds when the algorithm terminates. However, this false means that the stable property does not hold when the algorithm is initiated. We use this on definite is equal to true gives us that information about the state of the system at the termination of the algorithm, but this false gives us the information about the system state at the initiation of the algorithm. So the solution for the stability detection algorithm, recording the global state. Recording the this is shown here only. Record a global state S star, and definite is y of f star, we can say that. So the correctness of the stability detection algorithm can be considered as so S here S star, what S star is I already told. This is a global state is reachable from the initial state, and the termination state is reachable from the this S star state. S star means recorded state, and this y of s, I already told what y of s is. Y of s and y of s dash for all s dash that is reachable from s. This is from the, we already know, definition of the stability information. So here these two guys, Chandy and Lamford, that they in the 1985 only, they have come through with a brilliant idea of determining global state of distributed system. That will synchronize among the process in the distributed system by taking the snapshot of that recorded states of that one. Okay, thank you.